What is a black hole? Contrary to popular belief, a black hole actually has a very small radius in proportion to its enormous mass. A black hole also has a very strong gravitational force, one that is probably more than 1 billion times of Earth's gravity. This means it is probably able to suck in anything and everything you know, love, and care about. This may include your ex-girlfriend, the Eiffel Tower, and maybe even a small planet. Also, as we near towards a black hole and the gravitational force increases, we feel our weight change. So, in a gravitational field 10 times of Earth's gravity, a 70-kilogram woman would weigh a staggering 700 kilograms, which means, in a gravitational field 1 billion times of Earth's gravity, we would literally be crushing ourselves with our own weight before getting sucked into the black hole. A satisfying thought, isn't it? There are 4 types of black holes. The first type is called a Schwarzschild black hole. They are perfectly spherical in shape and do not rotate. The second type of black hole is called a Reznier-Nordström black hole. Similar to the Schwarzschild black hole, the Reznier-Nordström black holes are also perfectly spherical in shape and do not rotate. However, the difference is that they have an electrical charge. The third type of black holes are called Kerr black holes. Unlike the previous 2, they have the ability to rotate and are oval-shaped. The fourth and final type of black holes are called the Kerr-Nordström black holes. They have the same properties as a Kerr black hole, but also emit an electrical charge. There are also 2 other types of special black holes when quantum mechanics come into play. These are called the Planck mass and the primordial black holes. The Planck mass has a weight of 0.00000001 kilograms and a size that is 1 billion times smaller than a proton. A primordial black hole, however, is on the opposite end of the scale. It weighs a mass greater than 10 trillion kilograms and is extremely big as well. Primordial black holes are said to be formed directly after the Big Bang. Before we begin our interstellar adventure, there are a few mathematical constants which need to be identified. The mathematical constant G is the Newtonian gravitational constant, which equals to 6.67 multiplied by 10 to the power of negative 11 newtons, meters squared per kilogram squared. The second mathematical constant which will be explored is known as K. It is the Boltzmann constant and it is equal to 1.38 multiplied by 10 to the power of negative 23 joules per degree. The third and final mathematical constant which will be explored is commonly known as c, the speed of light. It is a staggering 3 multiplied by 10 to the power of 8 meters per second. And, without further ado, our interstellar mission will begin. For the first time in human history, the 4th of April 2352, we managed to safely send humans through and back from a wormhole. The astronauts on board the rocket were praised as heroes and were quarantined before they were let back to the public where they did countless media interviews. However, they brought back an undetectable disease which poisoned the air, and in a matter of a week, 1 billion people were dead. Soon after, another wormhole appeared. NASA believed that the only way to save humanity was to, again, travel through the wormhole in an attempt to find a habitable planet. The very few uninfected and alive humans who were left boarded an extremely fast rocket, traveled through the wormhole, but only to reappear right next to a supermassive Schwarzschild black hole. Now, we have to pilot the rocket out of the black hole to save humanity. We are the last hope. Firstly, we must identify the mass and the size of the black hole in order to escape its immense strength. The equation that defines the relationship between the mass in multiples of the sun's mass and radius in kilometers is r equals 3m. Using technology on board the rocket, the radius can be identified as 15 kilometers. Solving for m would give the result m equals 5, which means the mass of the black hole is 5 times of our sun. This is equal to 9.945 multiplied by 10 to the power of 30 kilograms. By fitting the mass of 5 suns into only a 30-kilometer sphere, it creates an incredibly dense force known as a black hole. Currently, our distance from the black hole is 5.6 million kilometers, but if we don't move quickly, we might soon be pulled into the hot gases and singularity ahead. But firstly, we need to check if the gas temperatures are getting too hot for the rocket. The rocket can only take heats up to 3000 Kelvin, or approximately 2727 degrees Celsius. The equation T in Kelvin is equal to 100 million multiplied by m divided by r cubed to the power of 1/4. By substituting m as 5 and r as 5,015 kilometers, the temperature is approximately 1299 Kelvin, which is equal to 1026 degrees Celsius. To find the minimum distance the rocket can get to the black hole, we need to solve for r in the equation 3000 Kelvin equals 100 million multiplied by 5 divided by r cubed to the power of 1/4. R is equal to approximately 1,834,404 kilometers, and we need to take away 15 kilometers, the radius, to find the distance to the edges or event horizon of the black hole. The final answer is approximately 1,834,389 kilometers. This means our rocket can afford to be sucked in 3,765,611 kilometers before it, along with all its passengers, get burnt beyond repair by the superheated gases orbiting the black hole. Now that we have identified the distance in which a rocket and all the passengers inside it will burn out, we need to use a formula to calculate the speeds we need to reach to be able to orbit the black hole. By substituting r as 5,600,015 multiplied by 1,000 meters, v equals to approximately 0.588 meters per second. This means our ship must move at 588 meters per second to stay in orbit around the black hole. But there's an emergency. The rocket doesn't have enough fuel to continuously travel at 588 meters per second. The rocket strays from its orbit path and heads towards the black hole. By using the formula E equals mc squared, we are able to identify the approximate amount of energy in joules that is being emitted from the black hole. The black hole's emission rate is calculated to be 8.95 multiplied by 10 to the power of 47 joules per second by substituting numbers into m and c. 2% of this is pure energy, and the rocket can only extract 10 to the power of -12 of pure energy per second. To calculate the total amount of joules that are going to be absorbed, we need to multiply the total amount of joules being emitted by 2% to find the amount of pure energy. Next, we multiply 10 to the power of -12 to find the amount of energy that our rocket extracts per second. The total amount of energy that is being extracted by our rocket is 1.79 multiplied by 10 to the power of 34 joules per second. This is more than an incredible 3.5 gigawatts per second. To put it in perspective, a gigawatt can provide energy for 700,000 homes for an entire year. As expected, the power lines for the rocket have fused, and now there is no hope. Once we reach the event horizon of the black hole, in order to stay in orbit or escape, we would need to travel faster than light, which would be impossible. However, if we could exceed speeds of light, we may be able to travel to alternate universes in the future using black holes as portals. But in saying that, the past 9 minutes and 30 seconds were all based off theory, as nobody actually has been through a black hole. So, don't take your failure to save humanity to heart. Thank you for listening, and I hope you enjoyed my video about black holes.